All right, so we're going to continue with intermolecular forces. We're going to focus just on liquids for a little while, and we're going to think about how intermolecular forces affect, oh, I know you love it, vapor pressure, boiling point, some things called surface tension, capillary action, viscosity, and so forth. Okay, so we're going to keep looking at these intermolecular forces. But first, I thought I'd think about what kind of liquids that you might know of right off the top. Of course, there's H2O, which I'm going to draw here. That's the most common liquid, obviously. But there are many others. For example, alcohol. Alcohol is a organic structure that has a condensed formula, something like this, or a formula. How about acetone, which is your nail polish or somebody's nail polish remover? And that has a structure that looks something like this. This is oleic acid. Every one of these corners has a carbon at it, and this is the chemist's lazy way of writing things. But anyway, all of this long length is one of the oils in olive oil, and that's a liquid under most circumstances. We know mercury is a liquid. We know that bromine is a liquid under most circumstances. Maybe you have hydrogen peroxide at home. So these are just some of the liquids that might be available to you on a daily basis, although probably not bromine. But most of these other things you could see a lot of different places. All right, so let's start with what surface tension is. Surface tension is an energy that you need in order to increase the surface area. All right, increase the surface area of some kind of liquid. Okay, so we're considering, for example, starting here. This is some water molecule inside of the liquid molecule. And it's surrounded by other liquid molecules, and it's being attracted or repelled by them, but mostly it's going to be attracted through those intermolecular forces. Up here, we have a molecule that's on the surface. What happens to these molecules? Well, in this case, the molecule is being pulled downward towards the particles, towards the liquids, okay, from the intermolecular forces. And it's sort of being against the air above it, okay. So surface tension is the amount of energy it takes to increase the surface area. So in terms of intermolecular forces, okay, increased intermolecular forces is equal to decreased surface tension. Well, actually, let me say this. No, I shouldn't say it that way. It's actually equal to increased surface tension because it takes more energy to get that molecule to leave the liquid state. Okay. So increased intermolecular forces means that the water or the liquid molecule is going to stay in the liquid. Okay. Decreased intermolecular forces mean that it would be easy for the molecule to escape into the gaseous atmosphere. Then there's capillarity or capillary action. All right, another result of intermolecular forces. And capillary action is the rise of a liquid against the force of gravity. So plants do this all the time. That's how they water themselves. They pull, through capillary action, water up from the soil. And what that is, capillary action, it's a competition between cohesive forces and adhesive forces. So cohesive forces means the ability of the molecule to be attracted to itself. Okay, so it's within the molecules being cohesed together, adhesive, I don't think cohesive is a word, but anyway. And adhesive forces are the attraction to the plant wall or the glass wall or whatever we're talking about there. Now, most liquids have a concave meniscus. A concave meniscus. Let me do this on this next page. Okay, most liquids have this concave meniscus, meaning that the water is attracted up the sides of the glass or silicone or whatever you've got it in. Okay, so it goes up the sides of the glass tube or whatever. In this case, this is a pretty wide tube, so your meniscus isn't that serious. You can see in a more narrow tube, you have a more pronounced meniscus. But mercury, okay, so this has the adhesive forces, adhesive, are greater than cohesive. And so therefore, the capillary action is up the tube. For mercury, the cohesive forces are the attraction of the molecules to each other and not to the sides of the wall. Mercury actually ends up having cohesive greater than adhesive. I got to write bigger, I'm sure. Adhesive. Okay, so in other words, that's a concave meniscus because the mercury would rather, with its intermolecular forces, is a whole lot stronger towards itself than it is towards any attraction to the sides of the wall. And this is just a typical paper chromatography experiment that maybe some of you have done where maybe you separated ions or something, and in this case the capillary action brought the ions up the page, up the paper. Okay, so these are intermolecular forces that are working against gravity. All right, the stronger the intermolecular force, the higher in capillarity, the higher the liquid can rise up the capillary, if it's a plant or a tube of water or whatever. Here's another example of something that's a cohesive force. In this case, these water molecules, these dewdrops that are sitting on some plant, are attracted to each other more strongly than they're attracted to the plant, and they stick together as long as they're kind of small. Okay, so you can see little dewdrops on things like that. Those are cohesive forces, strong cohesive forces, which means that the water is attracted to itself, or the liquid, whatever it is. Another thing liquids can be is viscous. Okay, and viscosity is resistance to flow. The higher the intermolecular forces, okay, the higher the viscosity. Obviously, we can heat stuff up and the viscosity gets easier, but the more intermolecular forces, the more viscosity there is. And so a classic example of viscosity would be how honey pours. You could pour honey, it'll pour out kind of slowly because those are pretty strong intermolecular forces and very long chains. So lots of London dispersion forces in there versus water. Okay, water has, relative to honey, has low viscosity, has high intermolecular forces, but it flows pretty easily compared to honey at any rate. So that's a property of a liquid. And then here we are back to these liquid, gas, vapor pressure business. Okay, just one more time to remind you. With the liquid gas, the higher the intermolecular forces, okay, so then this one will say this one has high intermolecular forces. Okay, and so there's very few gas molecules coming out of the liquid and into the gaseous space. For low so high intermolecular forces, low vapor pressure. If you have low intermolecular forces, something like oxygen in water, for example, then there's going to be lots and lots of gas in the vapor phase, so high vapor pressure. Now water, I know, I love water, don't you? That's very unique. And we know that it has intermolecular forces that are relatively strong, okay? It has lots and lots of hydrogen bonding. In fact, I wanted to show you a picture, okay, where we can see that water, this is a sample of water, and you can see that there's a very nice network. All of these are interacting with each other in some form, okay? So water forms this very arrayed and orderly kind of solution, and it's a great solvent. But let's go back here for a minute. Okay, so we've also learned somewhere along the way that the density of ice is lower than the density of liquid, which is good. That way we don't have a frozen world. Water is a really super solvent for polar molecules and ionic molecules. It's not that great for nonpolar molecules like, for example, the oleic acid or in the olive oil. It has high adhesive and cohesive properties. It has a very high melting point and a very high boiling point, much higher than we might have thought, given our other information because of those hydrogen bonds. It has high surface tension. And also water is really important in moderating our weather and climate. All right, so here's this hydrogen bond business again. I wanted to show this to you because I wanted you to see although these are bonded, the oxygen to the hydrogen, that's oxygen, that's hydrogen, those are bonded. This hydrogen bond between the hydrogen or the partially positive end of water and the partially negative end of the other water is very strong. And you can see that in any given water molecule, you can get quite a bit of charge interaction, making this, again, a very tightly kind of woven liquid. Now, I wanted to show this to you one more thing. Here's our water molecule, like so, and I wanted to show you the difference in the forces. So the bond between the oxygen and the hydrogen in water is 110 kilocalories per mole. Look at what this hydrogen bond is between these two different molecules. Okay, it's only about 0.4 kilocalories, but that's still very strong, especially if you add lots and lots of water molecules together. Okay, so that you get this interaction of a strong array of water molecules. Finally, ice has an open structure because of these hydrogen bonds. Okay, so because it has an open structure, okay, so you can see that it's layers and layers and layers of water molecules upon each other, but because of hydrogen bonding, that ice is less dense than liquid water. And of course, every snowflake, a whole series of water molecules put together, has its own characteristics, but they're just pretty to look at. And then there's this table in your book that talks about the properties of water, okay, and how important they are. They are very great solvents, okay. For example, they have all the ions that you need in water. There's CO2, there's oxygen. Our body carries, our proteins and sugars and so forth around. It has high heat capacity. That specific heat, remember, C, and the delta H of vaporization. Okay, so that allows us to have a narrow range of temperature for us to live at and for the Earth to operate at. It has high surface tension and capillarity so that water can be pulled up into plants through capillary action. And then, of course, the open structure of ice allows for the ice to be on top and the nutrients to still come through into the lakes and oceans and so forth. Anyway, so we'll have 2 more things to do in this unit, and then we'll move on. But I guess we'll finish these up before we move on, obviously.